Good evening, one and all. Already many number of participants has already joined. So let us start without any delay. Welcome to day 5 ATAL FDP on Industry 5.0 and Smart Manufacturing, organized by KIIT, deemed to be University. Today we have Dr. A.K. Sahu among us as our keynote speaker. Dr. Ashok Sahu is the Director R&D Technology at KIIT deemed to be University. He has extensive teaching, research and administrative experience of 24 years. He was the former Dean and Director of the School of Mechanical Engineering from 2014 to 2020. Dr. Sahu has published more than 150 research articles and 8 patents in his name. He has successfully completed 4 sponsored research projects from DST, SERB, and RPS AICT in the areas such as sustainable machining, composites fabrication, and machinability spray impeachment cooling, etc. Dr. Sahu is the fellow member of Institution of Engineers India and life member of IET UK, ISTE, and Indian Science Congress. May I now request Dr. A.K. Sahu to deliver his talk on the topic additive manufacturing and condition monitoring, smart manufacturing. Please, sir.
Thank you, madam. Good evening to one and all present here. And thanks for giving the nice introduction about myself. I am Dr. Is it audible, madam?
Yes.
It is audible to you?
Yes, sir, audible.
Yes, sir, audible.
Okay, please. So today I am going to deliver my research topic basically on the additive manufacturing, machining and machinability and aspects of additive manufacturing. Along with, I will focus on some concept about the tool condition and surface condition monitoring of the cutting tool during machining or during the hard machining. And as of all, we will discuss about the smart machining in details. So let me share my slides. Is it visible to one and all present?
Yes, sir. Yes, sir.
Yes, sir. It is visible.
Yes, sir. Visible, sir.
Okay. Thank you very much for your good attention. Yes, I am going to deliver my topic on machinability of novel additive manufactured titanium alloy and condition monitoring aspects using vibration signals, particularly in the hard machining area. Myself, Dr. Ashok Sahu, Professor, School of Mechanical Engineering, and currently I'm a Director of the R&D Technology in KIT University. So I will be focusing on the 2 major aspects. One is machinability aspects of some of the cutting tools, particularly the coated and uncoated carbide cutting tools during the smart machinings. And also I will be focusing on another case study related to the machinability of additive manufactured titanium alloy, its development, fabrication and machinability characteristics. And third case study, I will be focusing on the tool condition monitoring aspects using vibration signals during the hard machining study. So this is the 3 case study of the research that I am going to present in my talk. So let me go through the details as you know all about the manufacturing, that it is simply defined as a value addition process, that we know that it is a conversion of a raw material, improper size and shape of a raw material into the high utility and high value product. That means it adds the value to the manufacturing processes. In general, we can say that the manufacturing is a value addition process where it undergoes the several manufacturing process cycles, starting with the raw material. It has to be preformed first because it has to be preformed through different manufacturing processes like casting, forging, rolling, extrusion, etc., to get the near net shape product, that is called the preforming. As of you know, that the preformed part does not give the required dimensional accuracy, surface quality, and as such does not have the good surface quality, so that it does not serve any purpose to the engineering application. That's why it needs to be finished, and this semi-finishing operation is normally done by the process called the machining. And if you are to add if you want to enhance the properties of the work material like hardness and also wear resistance, corrosion resistance, etc., needs to be heat treated. Then after heat treatment operation, also the material is to be finished by the process called the machining. After that, it will undergo the super finishing process by lapping and honing. So it has a long manufacturing cycle setup and the costly set of equipments, etc. So inspection has to be carried out at each and every aspects. So machining is an essential and common manufacturing process of semi-finishing and finishing the pre-formed plant. What do we ensure? Actually, it gives the required size, dimensional accuracy, it satisfies some function, it prolongs the service life, performance improvement, and also the surface quality. As such, the preformed parts needs to be finished by the process called the machining to get the high quality, high utility, and high valued product. So machining is an essential and common engineering process of semi-finishing and finishing the preformed blank to desired shape and size with good surface quality by removing the extra material in the form of chips with the help of the cutting tool that moved past the workpiece in a machine tool environment. That's what you know. And also it has performed with several cutting tool, maybe a single point cutting tool, maybe a double point cutting tool like a drill bit, or maybe a multi-point cutting tool like milling cutters. So the geometrical aspects of the cutting tool, if we say that it is a single point cutting tool, the mechanism of the chip formation, particularly at the 2-3 point, whether it may be a single point, double point, or multi-point, is more or less same. As we know that the cutting tool plays very vital role in the machining and machinability study, any work tool combination pair. So we have to go through a little bit of discuss about the salient features of the different cutting tool, which is especially used in manufacturing, whether it may be a positive rake tool, whether it may be a negative rake tool, or as such, this tool is designated in different system of references. One is the tool in hand system, where it gives you only the salient features of the cutting tool like rake angle, clearance angle, and the principal cutting edge angle, auxiliary cutting edge angle, and the nose radius. And as such, the two most important angle who play very vital roles in the machining, that is the rake angle and the clearance angle, which is essential provided to allow the chip flow in convenient direction, and the clearance angle is provided to avoid the robbing between the work tool interfaces. And it has several geometry like positive rake tool, or it is a negative rake tool geometry, or it is a zero rake tool is provided, and clearance angle is essential provided to avoid the robbing. And it is must, and it is designated in different system like American Standard Association in ASA system, where you can, or it is called the machine reference system or XYZ reference system, where you will get the different angles in different views. In case of the machine longitudinal view, or it may be a machine transverse plane view and a reference plane. So there are the three planes: reference plane, longitudinal plane, and also the transverse plane, designated by the pi r, pi x, and pi y plane, and x, m, y, m, z, m axis. And there are the 7 angles which are associated with the different planes, and these angles are gamma y, gamma x, y, alpha x, phi s, r. So these are the tool nomenclature which is designated in the ASA system. Similarly, the tool is also expressed in ORS, orthogonal rake system, in 3 different planes. One is a reference plane, then is orthogonal plane, then is a principal cutting plane, which is along the direction of the principal cutting edge, and orthogonal plane is the perpendicular to both the planes. And the tool geometry is designated in orthogonal rake system where you can get the different angles in the different planes. In case of the principal cutting plane, you will get the inclination angle. In case of the orthogonal plane, we will get the orthogonal rake angle and orthogonal clearance angle. And if you will cut the view of auxiliary orthogonal plane, where we can get also the another clearance angle, that is called the auxiliary orthogonal clearance angle, and the tool is designated in ORS system, and the angles are lambda, gamma O, that means inclination angle, orthogonal rake angle, orthogonal clearance angle, and auxiliary orthogonal clearance angle. Auxiliary cutting edge angle, principal cutting edge angle, nose radius expressed in mm. Similarly, the tool is also expressed in the NRS system, normal rake system. Also, the 7 angles are associated with it, that is lambda, gamma n, alpha n prime. So these are associated with the normal plane, and normal plane is the plane which is normal to the principal cutting edge, is different than the orthogonal plane. And this is the geometry and the mechanism of the chip formation, that we know always the cutting tool is subjected to under compression first at the tool tip points. So during the compression, the shear stress develops, during which and whenever and wherever the magnitude of the shear stress exceeds the strength of the work material, then the deformation takes place and it flows along the chips. The chip formation starts. So yielding takes place at the chip tool interface, that is called the shear zone, that is called the primary deformation zone, and where the work is converted into the heat, and tremendous amount of heat is generated at the primary deformation zone. And when it flows over the rake surfaces, due to the presence of the friction at the rubbing surface chip tool interface, so there will be another secondary deformation zone where again the heat is generated. So the total generation of heat at the tool tip point is the primary deformation zone, secondary deformation zone, and tertiary deformation zone. And this needs to be controlled by the application of the proper cooling and lubrication technique under different sustainable machining environment like dry machining, or maybe minimum quantity lubrication machining, or maybe nano-assisted machining, or maybe flood machining. So you have to control the temperature at the tool tip points by applying the various coolants. And machining and machinability is the ease of the machining that we know, and it can be easily the ease of machining is usually assessed and judged by the magnitude of the cutting force, the tool life, and so the surface finish and magnitude of the cutting temperature, and the nature and form of the chip what is forming. And machinability is considerably high. We can say that when the cutting force, temperature, surface roughness, tool wear are very, very less, and the tool life is more, and the chips are short and continuous, providing the short chip tool contact length and less friction. If we observe this phenomena, then we can say that the machinability is good. And the cutting tool is usually failed by the catastrophic failure, by the different mode of failure, by mechanical breakage due to excessive force, stress, and vibration, or maybe due to plastic deformation due to stress and cutting temperature. If these two failures are avoided now due to the advent of advanced cutting tool materials, now another form of the wear, that is called the wear that is inevitable, which cannot be controlled, it is inevitable. And there are so many form and types of wear that is occurred at the cutting tool tip point during machining. One is flank wear, that is the axial, that is the crater wear. As we have observed, these are the nature of the pattern of the wear that is observed at the flank tool rubbing interface zone, and also when the chip is flowing over the rake surface. So there is a crater wear formation due to the adhesion and diffusion mechanism, and also there will be very small contact in between the auxiliary cutting edge point along with the work surface. So there is a auxiliary flank wear also. But out of these so many wear phenomena, the most important wear is the flank wear and the crater wear, which is formed due to adhesion, abrasion, and diffusion mechanisms in particularly. And it is the diagram that I have shown during the machining operation, where mechanism of the wear occurred due to abrasion, chipping, adhesion, and the crater wear, and also the flank wear BBC, which is a recommended limit of flank wear is 0 to 0.3 mm as per ISO standard for acceptable limit, and also for the roughing operation it may go up to 0.06 mm. So in order to have a good properties of the cutting tool material to reduce the to wear. So the cutting tool should have the strength, high strength, hot strength, and abrasion resistance, high hardness to resist abrasion wear, high hot hardness property, high fatigue resistance, resistance to adhesion and abrasion. So low thermal expansion coefficient, thermal conductivity should be high at the core and low at the surface. Chemical stability. So these are some essential properties of the cutting tool media should possess to avoid the tool wear. And nowadays, a commonly cutting tool material used now in machining operation is the carbide cutting tool material. So nowadays, coated carbide tools are extensively used in machining difficult to cut material, or maybe also in hard machining hard machining. And these coatings are usually applied at the substrate of the carbide interface. And this coating thins. Then hard thin layer coatings are nothing but the titanium nitride, titanium carbide, titanium carbonitride, aluminum oxide. And these coatings are provided in the range of 2 to 15 micron of thickness to the cutting tool by means of the physical vapor deposition and chemical vapor deposition techniques. I'm just showing the one case study between the comparative performance of the uncoated and coated carbide insert during machining of the hard material of the D2 steel, which is used in the machining operation. So let us see the actual machining and machinability observations, so that the cutting conditions that we have used, the workpiece that we have used in the D2 steel, whose hardness is 22 HRC, cutting speed is comparatively high, that is we have taken 200 meter per minute, and feed rate is 0.21 mm per revolution, depth of cut 0.4, and cutting operation is conducted under dry armament with two insert, that is uncoated carbide and coated carbide inserts. Responses, we have measured the flank wear, surface and cutting forces. This is the observation with relative to successive machining time the operation has been conducted, and cutting tool images have been captured by the tool microscope, where a lot of adhesion abrasions mechanisms are observed. As we have observed that during the 5 minutes and 3 minutes of time, the uncoated carbide fails and rapid tool failure occurs during 5 minutes of time, whereas the coated carbide insert, it undergoes up to 32 minutes of operation before attaining the required flank wear limit of 0.3 mm or to achieve the higher tool life. So this is a graph versus the progression of the flank wear with respect to the machining time and condition of the acceptable limit of the flank wear is taken at 0.3 mm as per the ISO standard, where it takes about 32 minutes to reach the tool life for the titanium nitride coated carbide inserts, where the uncoated carbide fails within 3 to 5 minutes during the machining of the hardened D2 steel. And the progression of the cutting force in 3 directions, in X, Y, Z direction, tangential cutting force, radial cutting force, and feed force are also captured by the crystal dynamometer, where you can observe the thrust force is maximum. That means Fy force in radial direction is maximum in comparison to the tangential cutting force and also the feed force. As because we have taken the depth of cut is very less, 0.4 mm in comparison to the nose radius 0.8 mm. So the cutting is taking place at the nose radius portion. That's why the radial thrust component of the cutting force are usually higher in case of the hard machining, as is clearly observed in the graph. Fy component is higher, but during the comparison of the uncoated carbide and the coated carbide insert, so we can see now the titanium nitride coated carbide inserts, it induces the less cutting force as compared to the uncoated carbide insert, where the cutting force is nearly 900 to 1000 newtons. So this is responsible for chipping and breakage of the cutting tool material due to the higher generation of the cutting force in machining of hardened D2 steel, whereas the ZRCN coated carbide insert, the titanium nitride coated carbide insert, the generation of the cutting force is around 160 Newton to 240 Newton. So that's it's comparatively safe. That's why the life of the cutting tool for the coated carbide insert is usually higher as compared to the uncoated carbide insert. So in order to compare the performance of the two inserts, so economic analysis has also been calculated, and the tool life of the cutting insert for uncoated carbide is 1 minute for failure, and also the titanium nitride coated is it goes up to 30 minutes to reach the flank wear limit of 0.3 mm. So the tool life is 30 minutes for case of titanium nitride coated carbide insert. So for the comparative analysis of economics analysis, as per the Gilbert's approach, so there are the different different cost component associated with the economic analysis, that is the machining cost, and this is the tool changing cost, and this is the tooling cost. So addition of the machining cost, tool changing cost, and tooling cost is called the total cost, machining cost per part. As it is observed, the total machining cost per part for the titanium nitride coated carbide insert is only ₹2 in as compared to the uncoated carbide insert, which induces 90.5% cost saving by utilizing the coated carbide insert in the machining of the hardened die steel in operation. So in conclusion of this case study, we observed that the uncoated carbide insert occurs or induces severe chipping, higher cutting forces, quick dulling of the cutting edges, and very low tool life as compared to the tin coated carbide insert, which induces higher surface quality, less cutting force, steady flank wear progression to achieve the tool life, so that tool life is higher, and 90% cost saving. So this is the benefit of utilizing the coated carbide insert, so as to get the higher machinability and higher tool life and the less cost during machining of the hardened steel. So this this paper has been published in the journal Measurement Elsevier. Let us come to the another case study of the hard machining. Nowadays, it is an emerging technology in the case of the machining industries or manufacturing industry particularly, because grinding is the preferred choice of the machining of the hardened component earlier. But due to the advent of the super hard cutting tool material and also the rigid machine tool, so the hard machining operation is successively replacing the traditional grinding operation. As we know, in the traditional grinding operation, so it has the longer manufacturing process cycle, costly support equipments, and also the costly grinding wheel cost, and also the cutting fluids are added during the grinding operation, so that it is not environmental friendly operation, not eco friendly. But due to the application of the hard machining, so it reduces the manufacturing cycle, reduces the cost, and also it is operated under the dry environment. So it is a cost saving, time saving, and also environmentally benign manufacturing. And nowadays, this hard machining is successfully replacing the grinding operation in many situations for any engineering application, particularly in automobile components, bearing material, and die and mold industries. So that's why hard turning is now emerging as an emerging research topic and research area in manufacturing fields. It has a lot of advantages that I have told: substantial reduction of the cost of manufacturing by reducing the cycle of the manufacturing, decreases the time of machining, improves the surface quality. It eliminates the coolant operation. That is the most important part, is extensively utilized in the grinding operation. And hard machining eliminates the long manufacturing cycle, and preferably cutting tool material used in hard machining is the cubic boron nitride CBN ceramic tools. They are popularly used. But nowadays, slowly, again the manufacturing cost has been reduced for hard machining by utilizing the coated carbide cutting insert, because the cost of the coated carbide insert is comparatively less as compared to the CBN and ceramic insert. However, we have to analyze the machinability aspects of the coated carbide insert so as to be suitable in hard machining. And these are the lot of applications, industrial applications in hard turning operation, in transmission of shaft, axles, ball roller bearing, crank pins, engine components. Some of the comparative features between hard machining and the grindings, and qualitative comparisons that is observed. But though it has a lot of advantages in hard machining as compared to the grinding, but there is always an uncertainty in application point of view in industrial application point of view, in spite of its effectiveness with respect to cost, time, and environment. So that's why, because to get the surface finish as compared to the grinding operation, whether the part accuracy or dimensional accuracy, what will be the tool life and tool wear in hard machining, particularly using the low cost coated carbide insert, and what will be the economical implications. So these are certain uncertainty always present in hard machining operation. So that's why research is needed, and research should be focused particularly on hard machining or in smart machining particularly, to so that the research should be focused on surface finish and integrity, tool wear pattern and tool life, force analysis, cutting temperature, chip analysis also. Optimization of the process matter is highly essential for effectiveness of hard machining. We have to correlation different mathematical and prediction models to be developed, and economical implications. So there are a lot of research gap in hard machining. That's why it is a burning topic now in the research of manufacturing area, particularly in sustainable manufacturing and the smart manufacturing, so as to get the benefit of it. So the most popular used coated carbide insert are less investigated in hard machining. That is the one of the knowledge gap or the research gap that we have observed. Dry machining is suitable for machining the hardened component due to thermal softening because the force is reduced. But at the same time, it increases the tool wear because the generation of a lot of temperature, due to which the tool wear is maximum, is higher, which deteriorates the tool life or drastically reduces the tool life and also the surface quality. These are the challenges. So that's why detailed machinability study on surface finish, surface integrity, and tool wear, tool life, etc. needs to be carried out using coated carbide insert, which is a less expensive cutting tool, and it should be implemented in hard machining for its effectiveness. The majority of hard machining operations are undergone in dry environment, and few studies were undertaken on application of the coolant. So there is a agreement and disagreement whether we will apply the coolants in hard machining operation or not. So this is also a burning topic and open to the researcher point of view also. Second thing, if you apply the coolant, suppose coolant is usually not suitable in hard machining operation, because if you apply the coolants in hard machining, a lot of temperature is generated. If you apply the coolants in flood machining operation, it induces the thermal stress, and maybe it may be a catastrophic failure to the cutting tool. So that's why there is a frequent failure of the cutting tool during the application of the coolant due to thermal stress and the catastrophic failure. So that's why whether it will be applied under the flood machining environment condition or it will be applied under the dry machining environment condition. So there is an agreement and disagreement. So we should always focus on in between. So there in between there is a dry and also the flood machining environment. So there is another most important techniques which is utilized for machining of this hardened component to get the effectiveness of the hard machining is called the minimum quantity lubrication methods. And very few works have been reported on application of also nanofluid nowadays. It is an emerging in hard machining and mostly MQL assisted, and it needs to be explored in other techniques. So these are the challenges. And also the optimization is highly essential. Despite the high potential of hard machining to increase productivity, to offset the environmental concern by dry cutting, its competitiveness with grinding process industrial application is limited. This may be due to uncertainty that I have described. And also another important aspect occurred in hard machining because the thrust force component is higher as compared to the cutting force and also the feed force. In particular in hard machining, because the radial component force is higher, which deteriorates the surface quality, deteriorates the dimensional deviation, and induces the vibration to the cutting tool, which needs to be monitored and controlled. That's why tool condition monitoring and surface condition monitoring study is highly essential for the machining of hardened steel or in hard machining in particular. So vibration signals have strong correlation with surface roughness and tool wear. So that's why tool condition monitoring study will be definitely worthwhile and beneficial for the application of the hard machining. So this is also a challenge. In MQL, heat transfer is predominantly in the evaporative mode, which is more efficient than the convective heat transfer prevalent to the current. So it is expected that MQL minimum quantity lubrication is a new strategy in which extremely small quantity of cutting fluid is applied to the cutting zone, and also it may enhance the machining performance beside adding the economical and ecological benefits. So needs to be investigated in details. Appropriate selection of a machining parameter, appropriate selection of the tool geometry, appropriate selection of the grade of the cutting tool material, appropriate selection of the coatings, particularly in carbide cutting tool inserts, are essential for suitability in dry, hard machining and smart machining operation. This brings the nobility of the investigation of the coated carbide insert in hard machining under a dry environment. So this is a challenge in dry hard machining, because there is an evolution of the cutting tool OER due to high cutting temperature. So proper and appropriate selection of the machining parameter, environmental parameter, as well as the geometrical parameter are highly essential for it. So heat generation during hard machining reduces the cutting force due to thermal softening and favors machining. However, tool life and surface finish deteriorates due to acceleration of the tool wear and built up edge formation. So minimum quantity lubrication plays very important role in this aspect. The study related to the machinability, modeling, optimization, sustainability assessment in hard machining is also lacking under dry and MQL environments, needs to be studied in details. Application of nanofluids in hard machining through MQL is also observed to be significant and emerging nowadays as a recent technology for cooling and lubrication, that is called the sustainable machining. Because it is nanofluids are especially applied due to excellent properties like thermal conductivity and viscosity. As far as hard machining is concerned, the application of the nanofluid assisted minimum quantity lubrication technique is very, very limited and thus needs investigation. So that's why I have shown here the different cooling and lubrication techniques usually adopted in hard machining. For its effectiveness are dry, flood machining, high pressure cooling, minimum quantity lubrication, nanofluid minimum quantity lubrication techniques, cryogenic coolings. So these are certain techniques that were applied. And sustainability aspects are needed and to be measured that for economical benefit, for environmental benefit, and for the societal benefit. So we observe the three important pillars in case of the hard machining, that is economical aspect, social aspect, and environmental aspect. Also, the carbon emission to be reduced for sustainability and noise emission to be reduced, and lot of economic analysis needs to be carried out for effectiveness of the hard machining due to nanofluid application, because a lot of costs are involved, because it involves the nanofluid cost, it involves the MQL setup cost, it involves the tool life, tool replacement cost, cutting tool cost, operator cost, and machine cost. So you have to optimize everything, economical aspects and societal aspect, and also the environmental aspect needs to be studied in details for sustainable machining. And a lot of costs are involved. As you know, the smart machining, if you want to achieve it, it has certain advantages which may result minimizing the tool path and machining time, improving the component of surface finish, maximizing the cutting tool life and cutting performances, machining complex geometrized components with improved precision and efficiency, like as the additive manufacturing, process optimization in light of autonomous sensings, self-learning and performance improvement in the process itself, sensing the cutting force dynamically, covering the cutting forces, chip formation, and interaction at the cutting zone. So these are some of the unique manufacturing advantages of the smart machine operation. Let us have another case study about the smart machining that I have observed, improving the component of surface finish. One aspect, improving the cutting tool life and also the cutting performances, and also minimizing the machining time and reducing the machining cost. So to achieve this smart machining operation, let us have one case study of the machining of hardened again D2 steel heat treated up to 55 HRC. The machining is the workpiece material hardness, which is operated under dry environment, dual nozzle minimum quantity lubrication environment. That means the double nozzles are applied. One is ejected at the flank wear rubbing zone and another is ejected at the crater wear surfaces, at the chip tool interfaces. Another is the flank tool interfaces. and also the nanofluid minimum quantity lubrication environment with ZrO2, zirconium oxide and nanofluid environment, and graphene oxide nanofluid environment. So 4 cutting environments are utilized for sustainability. So this is the experimental setup, and the cutting speed 80 meter per minute, feed rate is 0.05, depth of cut is 0.1, and 2 nanoparticles are used, ZrO2, zirconium oxides, and also the graphene oxides. Machining performances are measured here. Comparative machining performances are observed for the flank wear, dimensional deviation, power consumption, roughness, cutting temperature. Also, we have measured the carbon emission and the noise emission, as well as the chip characterization, also done by so many measuring instruments for microscope, surface roughness tester, IR camera, noise meter, then scanning electron microscope, and a lot of it. So this is the more or less the experimental techniques and setups. Minimum quantity lubrications, where the pressurized air and oil are forced through a specially designed nozzle, particularly at the 2 rubbing zone, that is at the chip tool interface zone and a work tool interface zone, and they are placed at 90 degree to each other, utilizing the 2 nanoparticle graphene oxide and zirconium dioxides. This is the setup of the minimum quantity lubrication application in the CNC lathe for smart machining operation with my setup. And this is the preparation of the nanofluids mixed with mineral oil LRT 30, then pre-disperming, then magnetic stirring of procedure followed by ultrasonication. Then nanofluids are prepared, and it has to be characterized. So many characterization of nanoparticles have been conducted through sediment test, pH test, spectroscopy, rheology, thermal conductivity, and tribological test, and also the toxicity property of the nanofluid has also been tested. Particularly 2 important property we have conducted here. One is thermal conductivity, viscosity, and toxicity property, also whether it is toxic to the environment or not. Similarly, for graphene oxide nanoparticle, we have prepared the nanofluid, graphene oxide nanofluids, and a lot of characterization we have carried out. And this is the experimental observation of the 4 cutting fluid environment in particularly hard machining, where flank wear progression with machining time, and it has been observed that at 0.5% graphene oxide nanoparticle due to application, the rate of growth of flank wear for graphene oxide nanoparticle in hard machining is comparatively lower as compared to dry environment, as compared to MQL environment, as compared to the ZrO2 nanofluid also environment. Similarly, cutting temperature are lower, and surface roughness are also lower, noise emission also lower, carbon emission, and also the power consumption during machining lower for the graphene oxide nanofluid environment at 0.5% of weight. And these are the EDS images of the cutting insert after machining with respect to the successive machining time at the end of the tool life, because the tool life for the graphene oxide nanofluid minimum quantity lubrication environment is found to be 136 minutes as compared to the 94 minutes for the ZrO2 environment. And further economic analysis has also been carried out for these 4 cooling and lubrication environment, where we can observe here the 0.5% of weight graphene oxide nanofluid minimum quantity lubrication environment gives the lower machining cost per part as compared to the other environment. Similarly, sustainability assessment has also been carried out using the POG matrix approach, where the total score has been calculated considering the different sustainable assessment parameters like environmental impact, operator safety, coolant cost, coolant recycling and disposal cost, surface roughness, flank wear, power consumption, temperature, noise level, part cleaning. So these are the sustainable assessment parameters we have considered for calculation of the sustainability assessment, considering environmental aspect, technological aspect, and societal aspect. And it's a qualitative approach where we can get the maximum score for graphene oxide and nanofluid environment. So it is more sustainable as compared to the others. So in conclusions, It is obtained that application of 0.5% of weight graphene oxide and nanofluid MQL environment, it provides better sustainability as far as socio-technological, economical, and environmental benefits are concerned as compared to the other environment from PUG matrix sustainability assessment approach, and it may be recommended to the machining industries for a green and sustainable manufacturing processes. So these findings are published in different ACI journals in sustainability applied sciences, and also the SAGE journal IMECI Part E, and also the Canadian Metallurgical Quarterly Journal in Taylor Francis. All are in ACI journals for sustainable machining, lubricants also, and it is published also in the IMECI Part E. So a lot of a lot of hard machining research articles that we have published under various sustainable machining environment under dry MQL and also the hybrid MQL environments, and nanofluid MQL environment also. The left-hand side, it is published in the Springer, that influence of aluminum oxide and titanium dioxide nanofluid in hard turning performance, and also in measurement Elsevier. Also, the paper has been published under measurement and machinability study under various environmentally conscious spray impingement cooling assisted machining environment also. So this is the recent articles that is published under application of the nano graphene oxide mixed dielectric in sustainable EDM of pneumonic alloy using copper and brass electrode. So this is the potential of application of the nanoparticle in dielectric or in the cutting fluid environment, whether it is a conventional machining or maybe a non-conventional machining environment. So let us go to another case study for additive manufacturing for the titanium alloy. So why this topic is important, that we know always, because whenever we go for the machining of the titanium alloy, it induces the lots of spark and also the fires, and also the temperature is maximum in case of machining of the titanium alloy, though it has a tremendous application in aerospace industries. It is very, very difficult and hard to cut material because the thermal conductivity is very lower and high chemical reactivity and work hardening property also. And whenever you machine the titanium alloys, it induces the built-up edge formation due to adhesion of the chip particle at the chip tool interface, which induces poor surface quality, dimensional accuracy, and thus in general, the tool wear is higher, and finally the machinability is poor. So these are some challenges in machining of titanium alloy. So to overcome it, the appropriate selection of the cutting tool material, cutting tool geometry, machining parameter, and appropriate selection of the cutting tool and the coolants are especially essential for the effectiveness of industrial applications. And as you know, the additive manufacturing is a smart manufacturing, is a process of adding material layer by layer from three-dimensional modeling. And evolution of 3D printing started when commercial 3D printer was introduced in the market in 2003. And this is the direct metal laser sintering process of the 3D printing operations. Subtractive manufacturing and the additive manufacturing. These are the components of the additive manufacturing. And the applications in various defense sectors, cranial plates, 3D metal printing products, very complicated shapes are obtained through 3D printers like DMLS method. And we know the titanium alloys are widely used, particularly in the aerospace, automotive, and biomedical industries due to excellent properties such as superior strength through weight ratio and corrosion resistance. Poor machinability titanium alloy is major concern. It is prone to high cutting temperature, high tool wear, and also the built-up edge, and the tool high level of tool vibration also that affects the surface quality. To reduce the cutting tool wear, chipping, and built-up edge, multi-layer coated carbide inserts are proposed generally. So coated carbide insert plays very vital role in this. In addition to this, and also various methods are adopted for development of the additive manufactured titanium alloy through direct metal laser sintering process. Okay, as observed from the literature, Additive manufactured titanium alloy have higher mechanical properties such as yield strength, ultimate tensile strength, and hardness as compared to the wrought alloys due to difference in microstructure that negatively influences the machinability. So there is a lack of ductility in additive manufactured titanium alloy as compared to the wrought alloy. Therefore, the need of machining of additive manufactured titanium alloys are gaining the importance nowadays. The rapid heating and cooling of additive manufactured titanium alloys during the 3D printing process, it develops the residual stress between the built part and object and within the object itself. So it needs to be relieved by stress relieving heat treatment process. The main limitation of the additive manufactured parts is the poor surface quality and shape accuracy, staircase effect because of high power laser beam to melt and fuse layer by layer of metallic powder together, and othering of non-melted powder particles to the fabricated components. This is a challenge. The poor surface roughness of additive manufactured parts depend on parametric settings such as powder size, scan speed, and layer height. So needs to be controlled the process parameter of the fabrication process during the additive manufacturing. Therefore, additive manufacturing processes are meant for producing the near net shape component. Thus, the optimization of the parameter setting in additive manufacturing may yield the better surface quality. So this needs to be investigated. Additive manufactured titanium alloys can be produced with higher strength, but the ductility and fatigue length are lower as compared to wrought iron due to high tensile residual stress, surface roughness, and porosity. Fatigue life also increases with the decrease of surface roughness. Therefore, the performance characteristics can be enhanced through additional heat treatment process for stress relieving. It has to be carried out. By using so, additive manufactured parts are now comparable with conventional manufactured parts. So post-process machining is essential for additive manufactured components to eliminate these problems. Further, additional surface machining is essentially required. Therefore, and also optimization of the machining parameter are also required to acquire the desired surface quality and dimensional accuracy for additive manufactured components. So that's why a case study is presented now here to know the machinability of additive manufactured titanium alloy, which is developed through DMLS method and compared with raw titanium alloy. This is the nobility of the research. Therefore, the research on machining of additive manufactured titanium alloy in recent years are gaining the importance. So this is the experiment conducted for the raw titanium alloy, and the experiment has been designed through Taguchi L18 orthogonal array by taking the three process parameter cutting speed, feed, and depth of cut with three levels 70 to 210 meter per minute cutting speed, and is operated on the flood cooling environment. This is the experimental setup for the machining of raw titanium alloy, optimized through grade analysis. This is the development and fabrication of the additive manufactured titanium alloy through DMLS method by different steps like a CAD model, then slicing of the model, then applying the process parameter of the additive manufacture. During the additive manufacturing, the titanium 64 powder it is, and also the 3D printing process is carried out. Then jobs are produced. Then it is heat treatment is carried out to relieve the stress, and finally the components are produced. So this is the experiment carried out in DMLS, direct metal laser sintering process, for the fabrication of the additive manufactured components by the DMLS method. So it is processed through the layer by layer depositions to get the components by direct metal laser sintering process. Then machinability has also been carried out with 3 process parameter with 3 level using Taguchi design of experiment. We have taken the L18 orthogonal array design of experiments under the flood cooling operations, and also this is the we compare the machinability characteristics also in 3 machining environment. One is dry machining environment, flood machining environment, also the MQL machining environment. This is the MQL setups. This is the measurement setup. This is the experimental methodology for sustainable machining under the 3 cooling and lubrication environment for the machining of titanium alloy. These are the experimental results and findings for the objective 1 for wrought alloy, where plank wear lies between 0.033 mm to 0.16 mm, where the acceptable limit of the plank wear is 0.2 mm that we have taken for finishing machining operation as per ISO standards, and surface quality acceptance limit we have taken as 1.6 micron comparable to the surface grinding operation as per ISO standard also. It is obtained, and a lot of adhesions, built-up edge formation, chipping, abrasion are clearly observed in the EDS analysis of the raw titanium alloy. Cutting speed is found to be most significant parameter for the tool wear. Feed is for the roughness, and the cutting speed is for the cutting temperature. As for the main effect plot and for the ANOVA analysis, the depth of cut and the cutting speed is found to be the most significant parameter for the tool wear progression, as the p value is less than 0.05 at 95% confidence level. Surface quality is obtained, and feed marks are clearly observed on the surfaces through metallurgical microscope, and also it is measured through the Taylor-Hobson surface roughness tester, where it ranges between 0.215 to 0.83 micron surface quality of array, average surface roughness, which is well within the 1.6 micron standard that we have taken as per ISO standard. And feed is found to be the significant parameter of surface quality in ANOVA analysis. For the cutting temperature generation during machining of titanium alloy through IR camera, it is within 31 degrees C to 150 degrees C. The maximum is 150 degrees C, where the plank wear is maximum. Depth of cut and cutting speed is found to be most influencing parameter for the cutting temperature generation due to machining of titanium alloy, as p value is less than 0.05 and contribution is maximum. Sawtooth chips are obtained. Optimize the process parameter. The level 1, your cutting speed, depth of cut of level 1, feed of level 1, and a cutting speed of level 1 induces the optimal machining process parameter for machining of titanium alloy, raw titanium alloy. Mathematical models are developed through quadratic regression analysis and found to be significant. Roughness model, temperature model, flank wear model are developed, and they are validated with respect to the normal probability plot, and model are found to be significant as the residual are lying over the straight lines, showing the accuracy of the models. Comparison between experimental and predicted results are also carried out, and they are very close to each other, observings. Then also we have conducted the machining for the additive manufactured titanium alloy and compared the result with the raw titanium alloy, where we have got the built-up edge formation in the optical microscopic image of the flank wear region of the cutting insert after machining, which has been carried out under L18 Taguchi orthogonal array for under flood machining environment. And where interestingly the built-up edge formation is almost seen in all the runs, as evident from the optical images. Adhesion, abrasion marks, built-up edge, crater wear, flank wear, chippings are quite observed in machining of titanium alloy. So needs to be controlled by application of the proper cooling and lubrication environment, like minimum quantity lubrication or in the nanofluid MQL environment. So the challenges are here and needs to be addressed, to be explored, so as to be suitable, so as to be effective machining of titanium alloy under different machining environment. Similarly, the parametric influences have been carried out for the titanium alloy, for the additive manufactured titanium alloy. Similarly, depth of cut and cutting speed are most influencing parameter. As per ANOVA, surface quality is very good. Cutting temperature generation are within 28 degree to 170 degrees C. And also the sawtooth chips are obtained, optimize the process parameter. Similarly, the level 1, cutting speed of level 1, feed of level 1, depth of cut level 1 are the optimal process parameter through Gray relation analysis. Mathematical models are obtained and correlation coefficient and R square value is very, very close to 1. That is almost 95%, showing the accuracy of the model. And also the regression models are significant because the p-value is less than 0.05. Normal probability plot, comparison between experimental and predicted value, they are also very close to each other, where the errors are found to be less than 5%. So mathematical models are found to be good for additive manufacturing titanium alloy. And a comparative performance have also been carried out under dry, flawed, and MQL environment at a particular machining parameter condition, that means depth of cut of 0.77, 0.1, feed of 0.1 mm per revolution, and cutting speed of 70 meter per minute. So at 70 meter per minute cutting speed, so we observe the less roughness, less flank wear, and less power consumption under MQL environment as compared to dry and flawed during machining of titanium alloy. Similarly, at 140 meter per minute cutting speed condition, and also the higher cutting speed condition also at 210 meter per minute with multi-layer coated carbide insert, where the evolution of the flank wear is 0.212 mm, which is well within below 0.3 mm for finishing operation, and RA value is 0.94 micron, which is well within 1.6 micron also under MQL environment, where we can observe that the under dry environment and flawed environment, particularly the dry and flawed environment at higher parametric condition, the VBC, the flank wear limit, is 0.484, and under flawed environment it is 0.416, which crosses the limit of acceptable limit of the flank wear as per ISO standard. So this under dry and flawed machining environment, so titanium alloy machining under condition is not suitable at the condition of the cutting speed of 210 meter per minute. So two layer progressions and optical images are clearly observed. Lot of abrasions, built up edges are observed, and surface roughness, where the depth of cut, cutting speed, feed are significant as per ANOVA, and feed is found to be most significant parameter. Flank wear, your cutting speed is found to be most significant parameter, and cutting power also, your cutting speed is found to be most significant parameter for cutting power. Models are developed, and also the sustainability analysis has also been carried out under 3 machining environment, where the sustainability score as per the POG matrix approach is higher under MQL environment as compared to dry and flawed. So these are some comparative graphs. So in general, in conclusion, that sustainability POG matrix assessment approach, it is revealed that MQL environment enhances the economical, technological, as well as environmental and operator health aspect also. Reduction of energy consumption by 53.96% and savings of carbon footprints by 68.46 kg of carbon dioxide emission observed under MQL at optimal condition, thus saves the manufacturing cost and carbon dioxide emission and satisfies the green manufacturing and the cleaner machining operation. These are some of the comparative result between the raw titanium alloy and additive manufactured titanium alloy, where the work has been published in various ACI journals in IMechE Part C and Part E of the machining of novel additive manufactured titanium alloy, which is developed through direct metal laser sintering process. The work that we have presented, the same findings that are reflected in these two journal articles. So last case study, we have to focus on the vibration aspects, tool condition monitoring aspects, considering the vibration signals measurement to monitor the tool wear and the surface roughness during the hard machining operation for the smart machining, because vibration plays very important role for the deterioration of the surface quality and also the growth of the tool wear and the tool life aspects in hard machining, particularly where the radial thrust component force are higher as compared to the tangential force. That's why some pilot test has conducted initially. This is the experimental setup where the accelerometer is attached, is mounted at the tool holder in both radial direction and also the tangential direction. The by accelerometer in Y direction and the Z direction is attached to the tool holder, and which and is the process through storage oscilloscope and vibration analyzer connected with the PC and analyzed through PC with the software. So we capture the acceleration amplitude of a vibration through time and frequency domain directly through the vibration analyzer with the PC, for which the machining length was fixed for the at 100 meter per mm at each and every run. The acceleration amplitude of vibration has been measured through accelerometer, vibration and signal FFT analyzer in both radial cutting force and tangential cutting force direction. That means we measure the acceleration amplitude of vibration in radial direction, that is Vy, and in tangential direction, that is Vz. Time and frequency domain waveform and spectrum obtained from single channel vibration signal analyzer that were processed through the software. So these are the readings obtained, the acceleration amplitude of vibrations. As we observe here now, the acceleration amplitude of a vibration are maximum under the radial direction. This is due to the higher thrust component force in hard machining condition, as you observe, as compared to the tangential direction. That's why in further operation of the machining of hard machining, we consider only the acceleration, we measure the acceleration amplitude of vibration only in the radial direction by conducting the experiment of Taguchi L18 orthogonal array, considering the three important process parameter: cutting speed, feed, and depth of cut. And the output responses are the vibrations, amplitude of vibrations, flank wear, and the surface roughness. So these are the exerts, and this is the time acceleration amplitude of vibration in both time and frequency waveform that is observed during machining operation at run number 1. At the time, the cutting tool OR is very minimal because it is operated at the lower cutting speed feed rate condition. So the waveform's amplitude of vibration is quite less. Similarly, it increases when the OR progresses. When it is operated at higher cutting speed of 147 meter per minute, so the amplitude of vibrations in both the domain, time and frequency domain, are higher, as it is clearly observed in both the waveform. And we developed model, first the linear regression model and also the quadratic regression model. First, we observed the linear regression model considering only vibration signal which are found to be insignificant because the R square value is very less and also the error are very larger. Then we developed another regression model considering the machining parameter and vibration signals. All four are taken together, therefore, to develop the regression model. However, before development of the regression model, it is essential to know about the significance of the correlation of the input parameter like depth of cut, feed, speed, and vibration on the output. For that reason, we analyze the Pearson correlation coefficient of input parameter, such as flank wire software. And it is obtained that for flank wire VBC, Pearson correlation coefficients all are positive and higher value. Feed is higher, next to acceleration, amplitude, vibration, next is depth of cut and cutting speeds are significant, all four, because they are all positive value. But for roughness, the cutting speed, acceleration, amplitude of vibrations and feed are significant, but depth of cut is not significant or not correlated because it induces the negative value. So acceleration, depth of cut shows the weak correlations with surface roughness as it becomes negative. Therefore, in regression models have been developed considering the important parameter only. And multiple linear regression models have been developed, which are also not significant because the errors are less. So that's why we have developed the multiple quadratic regression model, MQR model, for both roughness and wear, considering the machining parameter and also the vibration signals taken together, for which the regressions are significant. R square value is approaching to 1, and refined MQR model is developed, prediction models. R square is 98.6% for RA, and these are the residual plots for flank wear and the roughness. And experimental value and predicted value are compared, and percentage of error for flank wear is calculated. It is less than 1%, and percentage error for surface quality is less than 1.2%, that is 1.22% only for multiple quadratic regression model, MQR model, which is found to be very good. And these models are validated with with different combination of the parameters of cutting speed, and depth of cut, which was not chosen in the Taguchi design of experiment. And again, 3-4 experiments are conducted by taking the arbitrary parameters of the cutting speed and depth of cut. So 4 experiments are conducted for validation, where we obtain the percentage of error less than 5%, and models are found to be significant and good. And these are the waveforms obtained. Cutting speed found to be most significant parameter for the vibration. MQR model predicts well for the responses for both flank wear and surface roughness, considering the combined effect of machining parameters and vibration signals online in hard turning on the dry mode. So the models are validated, cutting speed found to be significant. Thus, a corrective measure can safely be taken in time during online prediction and control on the flank wear and surface roughness during hard machining operation with a reasonable degree of accuracy. So these are some of the journal articles that we have published, considering the tool condition monitoring aspects during the hard machining operation for both surface roughness and the flank wear. Thank you very much for listening. Thank you very much, madam.
Now, I request all the participants, if you have any query, please ask the sir. It is open for the open discussion. If anybody has any query regarding the topic, you can ask to the sir.
Hello, sir. Hello, sir.
Yeah.
Professor Patil here, sir. Sir, can you please explain in short how the validation has been done for whatever the models you have just made with the help of Taguchi method or predicted?
So the models have been done through the response surface methodology, okay, through quadratic regression model, okay, and these quadratic regression models that we have developed by taking the Taguchi parameter design, and conducting the experiment as per Taguchi orthogonal array, and the prediction models are developed, and some validation experiments have been performed with other combination of the process parameter which have not taken under Taguchi orthogonal array parametric design.
Okay.
Arbitrary setting, and the errors are less. So validation always to be conducted for other set of parametric condition, not at the set of condition parameters that we have.
Yes, sir. Yes. Okay, sir. Okay. Thank you, sir. Thank you, sir. Okay.
Any other questions? Perhaps there is no questions further. So thank you so much, sir, for your valuable talk and share your expertise with us. Again, I am very much grateful to you as you are coming to this place sharing something after after keeping my request. So thank you so much, sir.
Thank you very much. Thank you very much, madam, and thank you all the participants for giving me the opportunity to present my research to the August gathering, and esteemed professors and participants. I hope this will be. I think this. I think I have given a lot of information about the different challenges, and also the lot of research gaps and the gap and the knowledge gaps pertaining to the smart machining, pertaining to the tool and vibration aspect, condition monitoring in hard machining, pertaining to the different sustainable machining in order to enhance the tool life, considering different nanofluid, cutting fluid environment under MQL and different NFMQL environment, and sustainable machining as a whole. So different case studies have been presented here with the application of very inexpensive coated carbide inserts that we have not used the CBN and ceramic inserts. So thank you very much, madam, for giving me the opportunity to share my findings.
Thank you so
Thank
much.
you very much.
Thank you.